So, we're going to continue talking about some properties of liquids and gases and intermolecular force stuff. Just quickly, what are the three types of intermolecular forces? Oh boy. Dipole. And hydrogen bond. Okay, which one is the weakest? Okay, which one is the medium? Okay, and the strongest would be hydrogen. Okay, and what causes hydrogen to be the strongest of the three?
The difference in electronegativity.
Yeah, the biggest difference in electronegativity. Okay, now there is a certain situation where London dispersion can actually get relatively strong. What is that situation?
Larger molecules.
Okay, yeah. The bigger the molecule, the stronger the dispersion forces. And what was the main reason why?
Yeah, more electrons.
More electrons that could, get temporarily displaced, creating that charge, that momentary dipole. Okay. How does intermolecular forces affect properties like melting point, boiling point, things like that?
Stronger intermolecular bond, the more energy is needed.
Okay? So the stronger the intermolecular force, the higher the melting point, the boiling point, things like that, because you've got to put in more energy to break those stronger forces. Thus, it's going to take a higher temperature for those things to do that, for those things to break. What else? How does intermolecular forces affect viscosity?
Viscosity, resistance to flow. The higher intermolecular force, the higher.
Yep, the stronger the intermolecular force, the higher viscosity, because it's more attracted to itself and not attracted to the thing it's going to flow through or on or in. Okay? All right. Now, we're going to go again here, talking about a couple of vocab words that you have seen before. We're going to talk about the elusive vapor pressure a little bit today, do some math with that. But yes, you guys should be familiar with vaporization. It's just going from a liquid to a gas. But this is specifically evaporation is when it happens at the surface. Okay? Now it says up here that evaporation is, or vaporization is an endothermic process. Why is that an endothermic process? Yeah, right? In order to go from a liquid to a gas, we know gas has higher energy, and so therefore it's got to take energy in, making it endothermic. Okay? Now, we have also talked, and it's way back in chapter 6. Can you believe we're in chapter 10 already? I feel like that's long.
It's good one too.
It's like halfway through.
We didn't skip it. You knew it.
We just did them in like a day.
Yeah, because you knew it. That's not skipping.
No, I know, it makes sense. I'm saying that's why we're so far ahead. Okay.
Alright, so then we talked about enthalpy. And enthalpy was, essentially, if we're talking at constant pressure, it's really our heat. Okay, so this would be the amount of energy needed to take a mole of liquid and get it to vaporize. Okay, and again, this should also make sense. If we say high intermolecular forces means high boiling point, it would also make sense that high intermolecular forces would affect how much energy you would need to boil it. Right? No? Maybe? Yes?
Yes. You are correct.
I hope so.
I
Okay.
agree with what you said.
Alright, I want to show you a little visual. Open your book, page 471. This is kind of the elusive vapor pressure idea. Before I talk too much about vapor pressure, Water is a really unique substance. And I think I've said this before, like if we weren't so familiar with water on a regular basis, we would think like the properties of water was like the coolest thing ever. Like surface tension and how ice is less dense than the liquid form.
It's still pretty cool.
Yeah, it is still pretty cool, but I'm saying we're so used to it.
Yeah.
You know, the fact that ice is less dense is the reason why we can have aquatic life live through the winter. You know, versus freezing from the bottom up and then, you know.
Or being crushed by ice that sinks.
Yeah.
That comes off the river or something.
Yep. And so another thing that we a lot of times just don't think about is water has such strong intermolecular forces that it takes a lot of energy to evaporate it. Why do you think that would be significant? Why would that be something really important for just nature?
The ocean absorbs most of the sun's radiation and heat. If not, we boil to death.
Essentially. Yeah.
Yeah.
If first off, I don't know the actual percentage, but it's a large amount of our Earth is made up of water. I want to say something like 70%. That might be
something around there. Yeah.
It might be a little high. I don't know for sure, but it's an extremely large amount of our Earth is made up of water, and that water absorbs a whole bunch of energy without seeing a significant temperature change. Like we've talked about specific heat capacity and things like that. Well, if it wasn't the case, all the sun's radiation that we know goes into heating up water slowly would heat up the surface of our Earth, and essentially we'd be, you know, in a hot box sauna, and we'd probably fry to death. So water's pretty important.
Yeah. That's it.
Very important. You know, we don't even talk about the biological significance of, you know, our bodies being however much percent water.
We could overheat without that. We could overheat.
Water's pretty amazing. Okay, so let's talk about how vapor pressure of water works. Okay? This is kind of where I don't think I've stated the word equilibrium much up to this point, which is really whole second semester. But this is, you're gonna see the word equilibrium here. It's getting closer to equilibrium stuff. So yes, you'll like it. You'll like it.
That chapter was overrating last year.
It was overrated.
Like, yeah.
I blew it out of proportion. It made it hard.
I did not have.
You know, maybe the teacher was just really good at explaining it.
Yes. That's not our time.
No, but the second semester is fun because it is a whole bunch of equilibrium, but it's more mathy, which I guess for some of you guys that's better than others. But
As in less concepts or less vocab?
well, it's the thing with equilibrium is it's all the same idea, just in different situations. Like the concept of equilibrium doesn't change. Right? But you can apply equilibrium to acids and bases, you can apply equilibrium to all kinds of different situations. The concept is still the same, it's just, you know, in a different situation. But anyways, so if you look at this visual on the bottom left, 10.38. Okay, this is kind of interesting to think, but if you were to take liquid water, put it in a enclosed chamber like that, and let it sit, did you guys know that the level of the water would decrease? Now, probably not enough to really notice, I don't think. Like if we actually took and, you know, put water into an Erlenmeyer flask and corked it, I don't know if we'd be able to see the decrease in its volume.
Wouldn't the cork also absorb some of the water?
Maybe a little bit. Also, I think in a case like this, they're assuming that you're putting in water into almost a near vacuum like Erlenmeyer flask, because if you had atmosphere in there, it would change this a little bit. But so what they're trying to say is when you put water in a particular Erlenmeyer flask, what you have is you have an initial amount of water that what? What does okay, evaporates, right? Okay? Now, this probably isn't going to be earth-shattering news, but the amount of evaporation that occurs is dependent upon the temperature. The higher the temperature, the more things evaporate. The lower the temperature, the less things evaporate. Okay? And it's actually constant at a certain temperature. So if I'm at 25 degrees, there's only a certain amount of evaporation or a certain rate of evaporation that you'll have. It's not going to change, go up and down. It's a constant rate. This is how much evaporates. Okay? So initially, actually, you flip the page, you can kind of see this. Flip the page. You got a little table there on 472 at the top. You can kind of see a blue line and a red line. The blue line represents the rate of evaporation. Rate just simply means what? Speed, right? So how fast it evaporates. And I said that is constant at a specific temperature. Okay? Well, as things are evaporating, you're going to start seeing more gas particles, correct? Right? As you know, I got this Erlenmeyer flask here. As liquid begins to evaporate, I now have more and more particles that are in the essentially the air. Okay? Well, then you start seeing the opposite process occur, where you've got water molecules that are in the gaseous form that come and collide with the liquid that's at the bottom, and thus the opposite process of evaporation happens, known as what? What's the opposite? Yeah, condensation. Okay? So as the water molecules in the air start to accumulate, what you see is the reverse process start to speed up. Okay? Believe it or not, there really is no process that's not reversible. And we'll talk significantly, heavily about that next semester when we talk about equilibrium. But every process is reversible. Okay? And so, as you can see, notice the rate of evaporation stays constant, okay, but as things are evaporating, you're getting more and more gas particles, which is going to speed up the reverse process. Why? Why would it speed up the reverse process? Yeah, right, I got more gas particles in the air, more likely for it to collide with the water, and then go back to the liquid phase. Okay? So as that happens, you can see that red little curved line starts to increase, increase, increase until the rate of condensation does what? Okay? Reaches the rate of evaporation. So essentially what you have is water molecules evaporating as fast as gas molecules are what? Condensating, reaching a state of equilibrium. There it is. Okay? Now equilibrium is a dynamic process. Do you know what I mean when I say dynamic process?
Both halves are moving, but
Okay, not static, yeah.
both
What?
halves moving is not
Moving, right? It's a working process. What I mean by that is when we reach equilibrium, it does not mean that the rate of evaporating and the rate of condensation just all of a sudden stops. You hear what I said? Okay? Well, Mr. Kramer, if it doesn't stop, why don't we see anything happening? Okay, this is equilibrium. Yeah, I mean, essentially you're getting gas that is evaporating as quickly as gas is condensating, and so what you have is no overall net change. So at a subatomic level, things are actually frantically evaporating and frantically condensing, but since they're doing it at equal speeds, at a macroscopic level to the human eye, we don't see anything. This is the same for really all chemical reactions. Okay, and we'll get into other chemical reactions that have this process, or that have a forward and reverse reaction. But okay, we talked about condensation. Okay, so vapor pressure is really what vapor pressure is is the amount of pressure that this evaporated gas exerts. Okay? And we said that the amount of, or the rate of evaporation is constant at a specific temperature, right? So if the rate of evaporation is constant at a specific temperature, then you should have a constant vapor pressure at a constant temperature, because you're eventually going to reach what state? Equilibrium state. Okay, once you reach that equilibrium state, you're not going to have any change, and so you're going to have you're going to have a constant vapor pressure. So there's going to be a certain vapor pressure at 25 degrees Celsius, a little higher vapor pressure at 35 degrees Celsius. It's going to continue to go up until you reach a certain temperature. Now, I don't know if you guys remember this or not, but boiling occurs. Anybody know how boiling and vapor pressure are related?
Remember, they are related.
They are related. You guys remember? This is
When it,
The gas is above it, like,
it's the
or
equilibrium.
equal with the. Or
Kind of.
Is the vapor pressure greater than something else, or is it
close.
equal?
So boiling occurs when your vapor pressure, or the pressure of your evaporated molecules upward, equals the pressure of the atmospheric pressure pushing down.
Oh, hence bubbles.
And so what ends up happening is you have enough pressure to push up the atmosphere to give yourself enough volume for a gas bubble to form in the liquid. Because if you think about it, if I got some beaker here, okay, what has more, what takes up more volume, a liquid or a gas?
Oh, gas. I was thinking less volume.
Gas takes up more volume, right? So if I take one water molecule in there that's in the condensed liquid form and I turn it into a gas, wouldn't it have to expand the volume of this particular liquid here?
Yeah.
Wouldn't that have to, in order to expand, you'd have to have enough force to overcome what? The atmospheric pressure. And so boiling actually occurs when you have enough vapor pressure that can push up and displace the atmosphere above it. I know that's kind of weird to think about, but
That's why lid would be make it faster.
that's why what?
Putting a lid in the pot make it boil faster.
Well, I mean, it makes sense.
Because you're reducing the environment.
Yeah, you don't have the effect. That's probably as great of effect for
Yeah,
atmosphere.
the vapor doesn't escape as much.
I don't want to say that it's a significant effect, because it's not like if you take the top off all of a sudden stop boiling.
Yeah.
You know what I mean?
Yeah.
So I would say it might have a little effect, but I wouldn't say it's
Not a lot.
super great, because you can get an atmosphere that still can get in there.
But like things,
It doesn't dip as well.
What?
like things boil.
It's the whole thing boils up faster.
Okay, so this should also make sense here, this relationship. Notice that there's a lot of things that we have to know the relationship intermolecular forces play with melting points, boiling points, with now vapor pressure, with enthalpy of vaporization, how intermolecular forces impact all of those things, okay? So large intermolecular forces is going to mean low vapor pressure. Can someone explain why high intermolecular forces are going to mean that you're going to have lower vapor pressures? Don't overthink
It
this.
takes more energy to make it a vapor.
Sure. I mean, essentially, the stronger forces, the more energy you're going to need to vaporize it. And so you're going to have less vapor at a specific temperature because you're not going to be able to break those particles up at lower temperatures. This should also make sense why large intermolecular forces result in high boiling points. Because what does a vapor pressure have to do with boiling point?
It has to be high enough.
We said boiling occurs when the vapor pressure equals the atmospheric pressure. And a high intermolecular force is going to keep the vapor pressure lower, which means it's going to have to reach a higher temperature for it to actually get to the point where those are equal and boiling will occur.
So in Colorado, things boil
Or at a lower, not faster, just at a lower temperature. Yep. How significantly different the temperature is, I don't know. A couple of degrees, I wouldn't expect it to be a huge amount.
Some recipes do like have a liquefaction. I've seen a few that have like at this, if
if you're at this altitude,
Yeah.
make sure you only boil it for 4
Well, then
minutes.
they have one for like super low places too, and it's really weird. But it was, I think it was supposed to be a joke. I couldn't tell. It was. I printed the recipe off.
I mean, maybe. I'm sure, usually when you make food, you can cook it 5 minutes long or 5 minutes short.
Yeah.
It wouldn't be like that.
It was off the internet. So
Okay.
I couldn't tell.
So here is an equation that we have to do vapor pressure. I'm actually going to give you an easier one, or one you're probably going to use more. Okay, so I don't think you have this one. You're going to probably want to write this one in. So this is going to be the vapor pressure at temperature 1. This is the vapor pressure at temperature 2. And just for, just so you're aware, this is the R. I think we have used this R before, but it's not the 0.0821 R that we use for gas laws. Have you seen this one before? I feel like I have shown you this R before, right?
3.3.
No? Maybe that was just in physical science, or not physical science, in regular chemistry. It's been a while. Okay, so essentially what this is if we know the vaporization and our temperatures and one of the vapor pressures, we should be able to find at a different temperature how much vapor pressure it would have. Or if I know the vapor pressure of something is this much, then here's what that temperature has to be. Because remember, vapor pressure is constant for a specific temperature, right?
Yeah.
Okay? So this is going to be a relatively useful equation for us to figure out, okay, at a second temperature, what's my vapor pressure? Or if I have a vapor pressure of this, what temperature does it have to be? Okay? Now, if I get that, we're going to skip this. This would be, well, you'd have to look at, there's a graph in your book that wants you to be able to look at it and figure out which one has the higher enthalpy of vaporization. That would be just looking at the graph and seeing which one boils at a higher rate. We're going to get to do this problem here. Everybody get this equation? I do want to show you how to do this, and most of you guys are in advanced math, so taking anti-log is probably not very difficult, but just in case, we should do this problem. Okay, so we've got a few things here. We've got a certain temperature 1. Now, yes, we are going to have to turn that temperature into Kelvin. And the reason why we need to turn it into Kelvin is because our R value is in Kelvin. So this would be 298. What?
Sorry, I was seeing an example. It was a different example. It doesn't wear it right in my notes.
And then at that specific temperature, there is a constant vapor pressure, which is 23.8 torr. And we can pull out our 51st edition of Chemistry and Physics Handbook, and we can find the vapor pressure of water at that temperature, and that's what it would be. Do you know there's like 102 editions now of that book?
This one?
Yeah, of the Chemistry and Physics Handbook, the big one that I pull out for fun. What? I like the 51st. It's like 1980 something. All right, let's finish. Okay. There's our change in H. Ooh, that's in kilojoules per mole. What do we have to change that to? Okay, and then we got a T2 of 50, so add 25 to that, 323. Okay, so I'm just going to start erasing and plugging into that equation. Is that all right? And we know our vapor pressure of the first guy is 23.8. We're solving for the second vapor pressure. Our HVAP our R was that constant 8.3145
Joules per Kelvin.
Then we have a T1 and a T2. And then we would solve. For the sake of time here, I'm just going to give you what all of this would be solved, this right half side, what that would be. It would be negative 1.37. So then you have ln of 23.8 over PVAP at temperature 2. Okay, so in this situation, what we have to do is we need to remove the natural log. And I'm assuming a few of you at least know how to do that. How would we do that? Take the anti-log, and the anti-log of natural log is E. So, getting rid of this, I would have to take this E to the negative 1.37. That's how you remove ln. So you would get 23.8 over PVAP equals whatever e to the negative 1.37 is. I think it's like point. Is 0.254. And then you'd have to solve, just remember you cannot keep PVAP on the bottom here. That make sense? It needs to be on top. When you solve for it, you should get 93.7 torr. And that number should be higher than the previous number because as temperature increases, what should increase?